How does Gatorade fit in with AP chemistry? We'll find out today in aqueous solution. So let's jump right into it here. And so let's talk about what is an aqueous solution to start off with. And so an aqueous solution, as we covered in regular chemistry, so just kind of refresh your memory, is going to be a homogeneous solution. Homogeneous meaning it's consistent throughout, and we have water as the dissolving medium. So when we have something that's dissolved in water, and it's homogeneous, it's consistent throughout, we would have an aqueous solution. So a good example of an aqueous solution might be, let's say, some Kool-Aid. You take some Kool-Aid and you put Kool-Aid into water, and it all dissolves nice, and you mix it all up, and the top of the Kool-Aid tastes the same as the bottom of the Kool-Aid. We're going to have an aqueous solution. Let's talk about the difference between a solute and a solvent, and another thing from regular chemistry that we talked about. But a reminder for us. So our solute is going to be our dissolved particles. And our solvent is going to be the dissolving medium. So in our example of the Kool-Aid above, the water was our dissolving medium, and the Kool-Aid and the sugar and things like that are the dissolved particles. Now, typically in solutes versus solvents, the dissolved particles are present in a smaller amount, and typically the solvent is present in a larger amount, whether it be milliliters or whether it be grams. Okay, and these are aqueous solutions we're talking about, and we can have solvents other than water, but right now we're just going to focus on water. I threw out the idea at the beginning of Gatorade, and we've all heard about the electrolytic properties of Gatorade and why Gatorade is actually an electrolyte. And so an electrolytic property is the ability to conduct electricity, and Gatorade actually does have a little bit of the ability to conduct electricity. The reason why Gatorade can conduct electricity and why they market it as an electrolyte is for the presence of ions. And so what we're talking about is the dissociation of ionic compounds from a solid ionic compound into its ions. And so we have to remember what our charges are of those ions, and that's why we know how to look up charges on the periodic table, or why we memorize charges of polyatomics, because they often come up. So let's talk about an example of this, and a good example might be, and the example from Gatorade is one of the ions that are placed in Gatorade is nothing more than table salt. And so if we take table salt and we place table salt in water, and we have some solid table salt, what is going to happen is the table salt is going to ionize or dissociate. The force of attraction between the water molecule and the force of attraction between the ions is greater than the force of attraction between the sodium and the chloride. And so we're going to get sodium ions. Sodium is an alkali metal, so it's going to have a 1+ charge. And we know that because it's in group 1A. And if you don't remember that, go back and review the videos on how to calculate the charge of these ions. And we're going to write AQ because it is an aqueous solution. And then it's going to break up into the chloride ion, 1- because it's the halogen, and also an aqueous solution. Okay, and so if we were to maybe draw a little model of this, let's say a model. I'm going to try to draw a beaker here. And so our beaker's filled with water. There is our solvent, water. And if we were to put this in there, what we would have is, as we see above, we're going to have a 1-to-1 ratio of our sodium ions. Obviously, they're not going to be this big, to chloride ions. So to correctly model it, we would make sure that in here we would have a 1-to-1 ratio of our sodium ions to our chloride ions. Oops. Now I don't have the right ratio. And so let's put another sodium there. And so again, the reason for this is we have a 1-to-1 ratio of sodium and chlorines when they dissociate. And so that would be a model of this. And we're going to get more into this in a little while. Let's put a 1 there, put a 1 there. Okay, let's talk about what a non-electrolyte solution is. Now, An electrolyte solution is something that conducts electricity. Obviously, a non-electrolyte solution is something that does not conduct electricity because it does not have ions. And a great example of a non-electrolyte solution is molecular compounds or molecular compounds. So a good example of a molecular compound is sucrose. And sucrose has the formula of C12H22O11. And if we were to put sucrose into water, we know sucrose, sugar, it's going to dissolve. And so, but what it does not do is it does not break up into ions. It does dissolve, there's no doubt about that, and we've all experienced sugar dissolving in water, but it's not going to break up into its ions. Okay, and so if we were to model this once again, just like we did before, drawing a beaker, we could zoom in and see those individual molecules. Obviously, you'd have water as your dissolving medium, and then you would have your sucrose just sort of floating around in there. And there would be moles and moles of those sucrose atoms floating around in there, which is what would give it the sweet taste. But we do not have ions. You notice that there is no ion present up there, no positive or negative charges. Okay. Okay, the next thing we want to talk about ionic compounds in water. And the first thing, let's define what solvation is. And solvation is just when ions are surrounded by water molecules. And in order to talk about this, we have to talk about what is going on with a water molecule in its structure. So let's do that real quickly here. So we all know, of course, water is H2O. But if we were to draw kind of a ball and stick model of H2O, we would have our oxygen molecule here. And it's going to be single bonded covalently to a hydrogen. Actually, it's single bonded to two hydrogens. And I'm going to, for right now, leave off the unshared pairs of electrons on the oxygen because we don't really need to worry about that at the current moment. We will later on in this class. There we go. So in this molecule, one thing that we have to remember is we have to remember that the oxygen is more electronegative. And what does that mean? Well, it means when oxygen is bonded to hydrogen, and because oxygen is more electronegative, and we'll talk about the reasoning why it's more electronegative in a later video, but when it is more electronegative, it has the ability to attract electrons when it's bonded with hydrogen. So essentially, oxygen is pulling on all the electrons in this direction, and it pulls the electrons away from hydrogen, because it is more electronegative. Now, and what happens then in the water molecule is we get a slight negative charge on the oxygen because we have to remember that electrons do have a negative charge. And so there becomes a slight negative charge, and it's shown by writing a delta sign. So we say delta negative on the oxygen, and because the electrons are being pulled away from the hydrogen and we have the positive protons in the nucleus of the hydrogen is going to remain slightly positive, and both of these guys are going to be slightly positive. So what we have here is an overall neutral molecule that has a very slight charge of negative on the oxygen and positive on each of the hydrogens. Well, why do we worry about this? Is we worry about the orientation of how water orients itself around each of the individual ions. And let's talk about this. So example is if I take some solid potassium nitrate and I place it in water. So first thing we want to do here, and then we're going to bring this water back into it. And so let's take a look at just a balanced equation here. And so potassium nitrate has a formula of KNO3, solid, and we're placing it in water. And so what's going to happen is the potassium ions are going to dissociate, and they are 1+, and the nitrate ions are going to also dissociate, and they are 1-. Remember those polyatomics. You've memorized them. Do not forget about them. Okay, so that's NO3 right there. Let's just make sure that's written properly. Okay, now what would this look like in a model? Let's take a look first at our potassium ion. So if we have a potassium ion in solution, it's a 1+ charge. What is going to happen is the negative part of a water molecule is going to be attracted to it. So our oxygen, which is our negative part of a water molecule, is going to be attracted to this potassium, and not just one of them. It's going to there are going to be multiple molecules that will surround the potassium ion, and they surround it in this way because of the polarity of water and the opposite charges, because opposite charges do attract. So that would kind of be the surrounding of the potassium ion from water molecules because of the polarity. Now, if we take the nitrate ion has a negative charge. Now the water molecules are going to orient themselves in a different way. So now we're going to get the hydrogen being attracted to the nitrate because the hydrogen is slightly positive. And so maybe we have a hydrogen over here. And so you can see the difference in orientation of the water with respect to how it orients itself around a negatively charged ion and how it orients itself around a positively charged ion. This question was on the AP test last year. Students were asked to draw this, so it's a good thing to know. So you see the difference between the two. Okay. I do want to talk about something that's very important, and this is, let's get into the next part. It says, draw a particulate drawing of sodium sulfate dissolving in water. Now, of course, we remember all of our polyatomics, so we know that when let's draw a balanced equation for this first. So we're going to take some sodium sulfate solid, and we're going to place it in water. And so when this does break up, it's going to break up into the sodium ion, and it's going to break up into the sulfate ion, just like this. And these guys are going to be aqueous. This is going to be a 2 minus, it's a 1 plus, aqueous. Now, one of the things we need to remember is we need to balance this. So if we balance this off the other side, we have 2 sodiums per 1 mole of sodium sulfate. So this is going to give off 2 sodiums to 1 sulfate ion. So if we were to draw a particulate model, let's say we're drawing a particulate model of this, what's going on with this in a beaker. And there's my beaker. And of course we have water as our solvent. We have to make sure that we have a 2-to-1 ratio of the sodium dissolving with a sulfate. And so let's make sure we draw 2 sodiums for every 1 sulfate ion that's in the solution. Sodium, another sodium down there, and a sulfate. It doesn't really matter as long as it's 2-to-1 ratio. There we go. So we're good. Sodium sulfate 2-to-1 ratio is what we need to see occurring there, and that's what's happening with our particulate model. Now, we did talk previously already about what happens with molecular compounds in water. With respect to sucrose, we talked about that up above, so you can scroll back up and look what that looks like. It just, remember, molecular compounds are non-electrolytes, and which basically means there's no ions to help conduct electricity, like sucrose and water. Now, of course, we always have exceptions, as we'll find out that there's always exceptions in chemistry, and our exceptions are acids. And we remember those acidic molecules from regular chemistry often lead with a hydrogen, but not always, and then something else placed behind it. And we'll be talking more about acids in the days to come. And so let's say we take some hydrochloric gas and we bubble it through water. And so HCl gas plus H2O. Now, we might be tempted to say, hey, well, HCl that's a molecular compound. There's no metals in it. Hydrogen acts like a non-metal, so this is a molecular compound, but this is an acid. And so what happens with acids is oftentimes we are going to get ionization to various degrees. Hydrochloric acid turns out it's a very strong acid, so we will get a large amount of ionization or dissociation. And it's a 1-to-1 ratio, just like that. So there's our exception. We want to keep that in mind. If we were to draw a model of this, of course, again, real simple model. 1-to-1 ratio of hydrogen ions to chloride ions to hydrogen ions to chloride ions. Throw a 1-to-1 ratio in there, just like that. Maybe one more, and one more chlorine, or chloride rather. Okay, so it is all bouncing around. Okay, and obviously we're going to have water molecules that are going to orient themselves correctly around each of those. The last thing I want to talk about tonight is I want to talk about the difference between a strong electrolyte and a weak electrolyte, because there is varying degrees of ionization or solubility. So we'll talk more about this later, but let's get more into what's the difference between a strong electrolyte and a weak electrolyte. We say that in strong electrolytes we have these guys mostly dissociate, meaning they completely break up all the ions. Where let's say we have 1 molar hydrochloric acid would be considered a strong electrolyte, and that would mean that you would have 1 molar of hydrogen ions and you would have 1 molar of chloride ion, something like that. That is definitely a strong electrolyte, really going to dissolve, or really going to conduct electricity. Now, a weak electrolyte is something that's only going to partially dissociate. And what we mean by this is, let's say, acetic acid. When acetic acid is placed, acetic acid is the main acid that we find in vinegar. When acetic acid is placed in water, it really doesn't dissociate 100% of the way, meaning if we have a 1 molar solution of acetic acid, it doesn't necessarily mean we have 1 molar of hydrogen ions. Actually, we have a very small amount of hydrogen ions that actually are released. And so there's only a partial dissociation. And in this case, we call acetic acid a weak acid because it is a weak electrolyte. Sorry, we've got a fly buzzing around me now. Okay, I'm going to quickly sum up what we've talked about today. We basically have talked about how different types of compounds dissolve in water, ionic versus molecular. Ionic compounds, which we need to make sure that we balance our reactions and look at our ratios of ions. We talked about the orientation of water and how water is polar, which is slightly negative on the oxygen and slightly positive on each of the hydrogens, and how it'll orient themselves around. And we talked about electrolytes, whether they're strong or weak.